Hi, and welcome again to my physics short video lecture series. Today's lecture is going to be about continuity and energy in fluids. It is the first of our lectures on fluid dynamics. So we're going to be exploring the continuity equation or the continuity condition, and also the conservation of energy via Bernoulli's principle. Our first topic is the continuity condition. This is just mass conservation for fluids. You could think of this as being basically akin to what goes in must come out, or vice versa. So whatever comes out of a vessel, say a tube or a pipe or what have you, whatever comes out one end must have gone in the other end. In other words, we are not creating or destroying a fluid as it goes into or comes out of a pipe, hose, tube, whatever. Before we can unpack this statement in the terms of fluid flows, it's worth noting that we have an underlying assumption for these fluids. So the assumption is the fluid is not compressible. So that's an important assumption. Fluid not compressible. Now, all real fluids are to some extent compressible. So even a liquid can be compressed a little bit, but liquids especially, and supercritical fluids, that kind of thing, they tend to not be especially compressible to begin with, so this assumption is pretty valid for those. If you take other fluids like a plasma or a gas, those actually are compressible. This assumption could maybe be modified to say the fluid is not being compressed as it flows through whatever vessel it's flowing through. Okay, so a gas can flow with moderate to no compression through a tube, and so this continuity equation works out for gases as well, provided that we assume that it is not being compressed as it flows. There's some other assumptions that happen. We want in today's video to basically consider what is called an ideal fluid. An ideal fluid has a few properties. One of them is that it's not compressible. Another is that it's not viscous. And in fact, we'll consider viscosity in a future video. It is not turbulent, so there's no turbulent flow to it. Stuff like this. I should say here not turbulent. This basically means that the flow is what's called laminar. So this is basically what is meant by an ideal fluid. Now, as to continuity itself, let's come over here and discuss continuity. Continuity comes via the following equation. Let's define flow rate, and we'll define flow rate Q to be how much volume of fluid flows through a given vessel or what have you, a cross section, per unit time. In some sense, this line here already means the per, but we could say per unit time to make it more explicit. And this is through a cross section. Okay, so then in equation form, we would write a V for volume divided by a T for time. Okay, so what we've done here is we've defined a flow rate. Flow rate should be in meters cubed per second, but it could in principle be given in some other units like liters per second, so L per S, or liters per second. You could do gallons or quarts or whatever per second, centimeters cubed per second. Any of those are valid units for volume flow rate, but in order for everything else to work out in standard MKS units, probably you're going to want these units right here, meters cubed per second. Now let's consider a tube. Let's consider a tube that's maybe like this, and you have some fluid that's flowing through it, and the circle just represents a cross-section area. Okay, so this is cross-section area, and we'll label it as an A. Now your fluid is basically just flowing like this through this tube. How much volume per unit time is going to pass through this cross-section area? Well, it turns out that if we were to take this cross-section area and sort of extrude it to make it into a full volume like this, so this would be a volume of fluid, then this volume, V, would be equal to the cross-section area A times whatever this length x is. So we'll call this length x. So volume is A times x. That's just simply getting the volume of a cylinder for this tube, for example. Now we want to know the flow rate. That's a volume per time. So a volume per time, we divide some times out over here. Basically, x over t, this part right here, is speed lowercase v. So this is uppercase V for volume, this is lowercase v for speed. So we can say that Q is equal to V, the volume flow rate is equal to the speed times the time. Okay, that's a boxable equation. Now the speed would basically be the speed at which a given particle of the fluid flows. To use a kind of analogy, imagine that what you have is like a river. Okay, so there's a river here, and then you take a stick and throw it into the river, and so it's just kind of like floating on top of the river. But as the river flows, it pushes the stick along at some speed. That speed v that the stick is moving at is sort of akin to the flow speed of the water near the surface of the river. And there can be different layers, although for a tube like this with no viscosity, basically the layers all have the same speed, or at least we treat them as having the same speed for now. Okay, so now let's ask, what does continuity do? So continuity in this context says that Q in and Q out have to be the same. But that's the same thing as saying, if I have a tube, and it doesn't even have to be a straight tube, it can be wiggly like this, and it can even change in size. So here's my in and here's my out. Q in has to be Q out. But Q is V times A, so that means that lowercase v, the speed in, times the cross-section area in, has to be the speed out times the cross-section area out. Okay, so that's your continuity condition. Now note that this cross-section area is very clearly smaller than this cross-section area over here. That means that the flow speed here has to be very large compared to the flow speed over here in order for the amount of water or whatever fluid you have going in to be equal to the amount coming out. So sometimes this gets rearranged into something like A in over A out is equal to V out over V in, something like that. If you have a circular cross section, then you could also think of this as R squared in over R squared out is V out over V in, because the area of a circle is pi r squared. Okay, so that basically is your continuity condition. Your other condition is energy conservation. If I have some object and it's going to take some path, let's say that it starts off down here and it goes up the path. Down here maybe it has a speed like this, up here maybe it has a speed like this. we could determine whether or not energy is conserved by basically asking how much kinetic energy does it have. So 1/2 mv squared here, 1/2 mv squared here. We could ask how much change there is in potential energy. So let's call the potential energy down here mgh, up here mgh. Maybe this is initial, initial, final, final. And then we can also ask how much work has been done on this from here to here via, for example, somebody pushing on it. So somebody can come along and like push the object. Okay, so you have work is force times distance, and work up here, force times distance. It could be that somebody's up here pushing the other way. So your energy conservation for this system would look something like this: 1/2 m initial v, or mv initial squared, plus mgh initial, plus, let's say, F initial times D, we'll just assume that it's pushing directly on it, is equal to 1/2 mv final squared plus mgh final plus force final distance. Okay, now when we go to a fluid, this is all still basically valid, except for that, to make things easier, because you could pick any little particle of the fluid, what we do is ask in some sense how much per unit volume. So I'm just going to divide everything in here by a volume term. What is that going to do? Let's remember that mass over volume is by definition density. Okay, so mass per unit volume is density. So this term and this term and this term and this term cease to have mass and instead now have density in. Force per unit area is defined as pressure. Okay, now you may not see where there's a force per unit area because we said force over volume, but remember that area times depth is equal to volume. All right, so that means that this term right here could be broken into a force per unit area times a depth over a depth, and that's just the same thing as a pressure. Okay, so your energy conservation has become 1/2 rho v initial squared plus rho g h initial plus p initial, this is your pressure, is 1/2 rho v final squared plus rho g h final plus p final. Okay, this is now your conservation of energy. This is what is also known in fluids as the Bernoulli principle. So Bernoulli principle. Now between these two things, basically continuity and Bernoulli, between these two things, we're able to adequately describe the motion of any basically ideal fluid through a container. All right, so let's consider some examples, a few short examples to round things out. So first example, let's say that I have a container that does something like this. So I have an open end here that the fluid's flowing into, and then over here I actually run into a junction, and that junction is such that instead of having just one tube, I have two tubes at the output. Each one of these two tubes is the same size as this. So this area, and this area are all the same size. So this would be like A1, this would be like A2, this would be like A3, and we can say A1, A2, and A3 are all equal. Now let's say, for the sake of argument, that we're looking at this from above, so there's no height changes. And let's say that we have some speed right here. Let's say that V1 is equal to, I don't know, 1 meter per second. Let's say that the pressure on this end, P1, is equal to, let's say like 98 kilopascals. Remember that pressure is in pascals, so this is 98,000 pascals. Okay, so what we want to know is what is the speed V2 and what is the pressure P2, knowing that V3 and P3 will also be the same as the P2s and V2s. So to solve this, continuity says, so continuity, Q1 is equal to Q2 plus Q3. Why is that? Because this is what we have going in, this continues along to here, and then at this point it splits two ways. So if I have a liter going in here, I have a total of 1 liter coming out between these two openings. So half a liter could go here and half a liter could go here, for example. All right, but this basically means V1, let's call all these areas just A since they're all equal. That means that V1 times A is equal to V2 times A plus V3 times A. But remember that V2 and V3 are equal. Remember that we have A's in all of them, so all the A's could cancel. What we end up with is V1 is equal to 2V2, and therefore V2 is 0.5 meters per second. Okay, so we figured out what the speed is, so let's go ahead and write the 0.5 meters per second up here. To get the pressure, we now invoke Bernoulli's principle. So we have 1/2 rho V1 squared plus P1 plus rho GH1 is equal to 1/2 rho V2 plus P2 plus rho GH2. Now remember that we're looking at this from the top, so this is viewed from above. That means that all of these are actually at the same height. Remember that I'm only looking at the entry point here and the exit point here to solve this. I don't actually have to consider this part to use Bernoulli's principle, although this part will also be consistent with these. Okay. Again, I said that this is water. So water, we know that the density of water is 1,000 kilograms per cubic meter. Okay, so since the heights are the same, this whole term and this whole term cancel. You could think of this as being a delta H term distributed between two terms. Delta H is 0, so those terms go away. I'm solving for P2. So P2 is 1/2 rho V1 squared minus V2 squared plus P1. Okay, so now looking at this, this is 1/2 times 1,000 kilograms per cubic meter. These right here are 1 meter per second squared, and then 1/2 a meter per second squared as we solve for below or before. And then to that we're adding 98 kilopascals, so 98,000 pascals. All right, this right here, if you put into your calculator, this is 0.75. This right here is 500. So 0.75 times 500, when you multiply these two together, would be 375. Okay, so that means that P2 is 98,000 plus 375, and since everything's in kilograms, meters, etc., This is 98,375 pascals is my pressure at the output. All right, so that's a quick example that shows both continuity and Bernoulli in action. And that's all that I wanted to do in today's video. Thanks for watching.